Okay, section 2.4 starts talking about one-sided limits. And we talked a little bit about that on Tuesday when we talked about, oh, this limit doesn't exist because it's different on the right and the left. So you can have a limit just from the left or just from the right. And it's written, here's the little notation. If you are coming in from the right only, you will have a little plus above the number that you're approaching. If you're coming in from the left, it's a negative there. It's not really a negative sign, it's just an indicator it's coming from the left. So if you say limit as x approaches c from the right, you only want to look at it coming this way and say what's the limit. Okay? So for example, on this picture here, make this bigger. Okay, on this picture, this is a function x over the absolute value of x. Okay, if I said the limit as we approach 0, let's do it this way. Limit as x approaches 0 from the right, what's the limit? 1. But as we approach from the left, what is it? -1, okay? And so then the limit as x approaches 0 is what? Doesn't exist. Because the limits have to be the same. They have to be equal on the left and the right, okay? You can have a right side limit, you can have a left side limit, but for in general, they must be the same thing. So anytime you see this, it's not going to exist if you don't have a plus or a minus, okay? So, this theorem says it has a limit as x approaches c if and only if the limit exists and the limit from the left and the limit from the right equal each other. That's essentially what it's saying. So that's what makes it exist. Okay? All right. Then a couple of theorems that you just need to memorize. You just need to know these. The limit as theta approaches 0 of sine theta over theta equals 1. So when you're working with some things, if you can manipulate the function to make it look sort of like that, sine theta over theta, you've got it, because we know the limit as we approach 0 is equal to 1, and we'll do some manipulating of that. Okay, so that's an important one. And I put this example in here. I didn't give you one like this on your homework, so we'll go over it, but I think it's really expecting a little much from you. It was out of the book. It's expecting that you would remember the half-angle formula from trig. That's a big expectation if you haven't had it in a while, or if you haven't had it at all. That could be a problem. So let's just kind of go over this. I don't know that you want to write it down. You can actually print it later if you want to. It says show that the limit of as h approaches 0 of cosine h minus 1 over h is equal to 0. Okay. Well, we don't have anything about cosine h over h. But if we go back to the half-angle formula, 1 minus 2 sine squared h over 2 is cosine. Okay? So, and some of you, I can see, you're already just like, I'm out of here. So if we substitute this for cosine h, you actually have minus 2 sine squared over h minus 2, whatever, minus 1, and there was a 1 there. I left those out. They cancel each other. That's why I left them out, but I'll show you. Because you had cosine minus 1. So here's cosine, 1 minus 2, and then we had the minus 1. We substituted this much for cosine. Does that make sense? That's the formula for half angle. Yeah. Okay. 1 minus 2 sine squared of h over 2. It's a formula for half angle. Do you have it on the, are you looking at the trig sheet? Do you find it? Hold on, and I'll help you find it. Yes. Okay, so we've solved our dilemma of where this came from. It was actually a double angle formula, changed up a little bit, because cosine of 2 theta is equal to 1 minus 2 sine squared theta, and if you divide the theta by 2 there, and you can divide it by there, okay? So we've got cosine h equals that. So we're doing the limit as h approaches 0 of 1 minus, here's our cosine thing, and the ones cancel out, so they're gone, okay? All right. This is a negative two sine squared h over 2. If we let theta be h over 2, can we do that? Let theta be h over 2. And if that's theta, we have negative 2 sine squared theta. But what does h equal? If theta, you guys follow me. Okay, if theta equals, what did I say, h over 2? Theta equals h over 2. What is h going to be? 2 theta. Okay, so we got to make those substitutions. I kind of left out a little bit of stuff here. I'm regretting this problem. Okay, all right, so we've got the limit as h approaches 0 of negative 2. Why do I have 2 there? Was that from the thing? Okay. Sine squared theta over, what do I have here? 2 theta. Okay? All right. So now, where did this negative right here come from? The negative 2 over 2, can I bring that out? Think of this. Think of this. This is negative 2 times sine theta over 2 theta. Okay, does that make sense at all? Does that negative 1 come out? Okay, and so why did I break it apart to look like this instead of sine squared? What's our theorem? Sine theta over theta. So if I break it apart, I've brought the negative 1 out, so those are gone, and I've got sine theta over theta times sine theta. So what do we know this is equal to? 1. What is the sine of 0? Sine of 0. 0. Sine of 0 is 0. So negative 1 times 0 is 0. Okay? Long problem. You don't have one like it on the homework, so amen to that. Okay? No. If you don't see it, something like it on the homework, I'm very unlikely to give it to you on the test. Okay? So, no. No. All right, let's look at this one, because you do have something a little like this on the homework. Show that the limit as x approaches 0 of sine 2x over 5x equals 2/5. You have to manipulate this guy and get it to be sine 2x over 2x for our theorem to work, right? So we need a 2x down here. We need a 2x here instead of a 5x. So if you multiply the top and the bottom by 2/5, we make that happen. So we have the limit as x approaches 0 of 2/5 times the top over 2/5 times the bottom. Does that make sense? Because we're trying to make this be 2x down here. And if I multiply 2/5 times 5 over 1 x, I get 2x. Okay, so that's why I'm doing that. So I've got 2/5 sine 2x over 2x. How did I do this? You can bring that number in front out. That's one of those rules. So I had this 2/5 up here. I brought it out. 2/5 limit as x approaches 0 of sine 2x over 2x. What's the value of this? If you take the limit as x goes to 0 of sine of anything over the anything, what do you get? 1. So that's 2/5 times 1, which is 2/5. Yes, ma'am. How did we get that? 2/5 times 5x, which is 2x. Okay. Okay. All right. So that technique you're going to use on your homework. Thinking about, oh, I need to make the denominator this, and what can I multiply by it to get that? So that's a technique that we'll use. Okay? Everybody good with that problem? Are you still writing? If you're writing, I'll hold on.
Okay, wait, what did you do? Can you explain to me what you did? I got everything up to this nonsense here on the second step.
This nonsense?
Yeah, that nonsense.
Okay. This nonsense? Okay. All right. So, are you wondering where this came from?
Yeah.
Okay. I sure can, because you can't see that. Okay, so you're wondering where this came from, Leland. Thank you. All right. If we let me put another step in there, and then maybe that will be good. So when we did this, we ended up with limit as x approaches 0 of 2/5 sine 2x over 2x. Do you agree there? Okay. When you have just a number in front of this, you can pull it to the outside. Okay? So I brought the 2/5 out. Limit as x approaches 0 of what is left. And I'm there. 2/5 times 1. That's that theorem. That's just that sine theta over theta. The limit as we go there, as we go to 0. All right, is that better? If that had been a 5 there, I could have pulled the 5 out, and we'd have been okay. All right, let's go to the problems. And they start out fairly easy, which is good. Okay, use the following function to answer the questions. All right. Here's the function, and here's a picture of it. And we're going to use our picture. We do need to kind of mark on our graph because you can't see it very well. 1, 2, 3. This is x equals 3 right here. And 1, 2, 3, 4, 5, 6. No. 1, 2, 3, 4, 5. I don't know. I'm trying to figure out what that dot is. Okay. You can. You can. All right. Find the limit as x approaches 3 from the right. Well, here's x is 3. If we're coming in from the right, what's the y value there? 5. So the limit as we approach from 3 from the right is 5. As we approach from the left, that's coming in this way, what's that value? 3. Okay. All right. We good? You like those kind, right? Okay. Take out some room here so we can still see our picture. Does the limit as x approaches 3 exist? And if so, what is it? If not, why does it not exist? Doesn't exist, why? Right and left are different. Okay, so this is the way this is written. The limit as we approach 3 from the right and 3 from the left do not equal each other. Okay? All right. Find the limit as you approach 5 from the right and 5 from the left. So let's go back to our picture. Make it a little bit bigger. Okay. 4, 5. Okay, here's 5. And if we go up, right there's where we end up. And that is at 5, 6, 7. So just so you can see that. Okay, so the limit as we approach from the right is what? And the limit as we approach from the left? Okay, so we're going to go down and put that in our answer. So 7 and 7. Question?
How does it equal 7 on the other side?
Well, if you're coming in toward 5, if we're going to 5 this way, we still end up at 7. Oh, well, you're not, I mean, because what you need to do when you're approaching something is go on the x-axis. So as we approach 5 from the left, go up, where am I at for my limit? As I approach this way, go up. Okay, does that make sense? Okay, all right, so we're at 7 and 7. Does the limit as we approach 5 exist? If so, what is it? If not, why not? What? Okay, so we're here. Yes, it exists, and it equals 7. Okay. Number 2, find the following limit. Is there any reason as we approach negative 0.2 from the right, is there any reason we could not just direct substitute? I don't think so. Is that right? Try to do that on your calculator. But you know what? They don't want decimals. It says use an exact answer. So what you can do, you have, this was negative 0.2. Sorry. I just didn't copy that whole thing down. Go ahead and do negative 0.2 plus 11. What do you get? And negative 0.2 plus 2. Okay, now divide 10.8 by 1.8. 6. So your answer you would leave at square root of 6. Okay? Because he didn't want you to go ahead and tell me what the square root of 6 is, because it said do an exact answer using radicals as needed. So it's not a hard one. It's just you needed to pay attention to what they were asking. Everybody good on that one? We're still writing? Okay. Jeremy, you still writing? Or are you good? You're good? Okay. All right. The limit as x approaches c from the right, given that c is 8. Is there any reason we could not just direct substitute? No. So go ahead and do that. Plug in 8. It says type a simplified fraction. Doesn't want it decimal, wants fractions. Okay?
It didn't matter in this one.
Yeah. You are multiplying those. But remember that you got to have it in fractions. So did you get this? Did we get that? 224 over 81. What? Anybody have a question on that one? About what?
I was just saying, dimensions of from different pieces down.
It's not. It's not bad to remember how to do fractions too. But yeah, that's a right. I got you. I got you. Everybody okay? All right. Number 4 is using that technique we talked about, using the theorem that we want to remember the limit as theta approaches 0 of sine theta over theta equals 1. Okay? Of course, we're using y's instead of theta, but that's okay. What do we know? What do we need? The answer. We need 16y in the denominator to be able to use this theorem, because this amount and this amount have to be the same thing. Okay? So what will we do? We will multiply numerator and denominator by what? 16 over 15? Okay. So we'd have limit as y approaches 0, 16/15 sine 16y over 16/15 times 15y. And what do we get? Could we pull this 16/15 out, Leland? Isn't that very much like what we had before? So we would have 16/15 sine 16y over what? 16y. And that looks very much like what we need. We need that amount there, that theta, to be that. Doesn't that look like this? Okay. And this is still the limit as y approaches 0. Because when you look at something like that, if you don't have that theorem, then you're going to think, oh, I can't put 0 on the bottom of this. But it's that whole item, sine something over that something, that makes it go to 1. And there's a proof of that, but we accept it as a theorem. Okay? So what will our final answer be? 16/15. So limit as y approaches 0 equals 16/15. There could be. It could be. I would really not for you for right now, but there could be. Yeah, there might be other things going on in the function rather than this. You might have some other stuff, and so it could be affected. It could be affected. The limit as y approaches 0 of this is 1, and then 1 times that. Yeah, I just didn't rewrite the living thing over there. But yeah. Yeah. Okay. Question?
Yeah, okay. I get what you're trying to do by getting the 16 on the denominator, but I just don't understand how you come up with 16/15. That's probably
Oh, okay. All right. If you're wanting 15y to become 16y, I've got to multiply something by that to get there. So if I do 16 over 15 times that, what happens to that and that? Okay? So you kind of have to write it out and think about that this has got to cancel out, and I need this to be left. Does that make sense? Okay. All right. Okay. That looks ugly. Does it look ugly? Find the limit as x approaches 0 of x cosecant 11x over cosine 15x. Okay. Those are kind of different things, and we've got an x cosecant x. That's weird. All right, we got to remember a couple of things from trig. What is cosecant equal to? 1 over sine. Okay, So that's important. We can remember that. And according to the limit rules, we can rewrite this as two separate limits. Okay? So I could rewrite limit as x approaches 0 of the top over the limit as x approaches 0 of the bottom. And I want you to look at that bottom. Is there anything wrong with just direct substituting 0 in that one, in the bottom, in the denominator? Could we just plug in 0 for x there and be taking the cosine of 0, which is 1? So when we rewrite this, again, we figured that out. So now we have the limit as x approaches 0 of x cosecant 11x. So at least we've eliminated the bottom part. Is that good? Well, I guess I just showed you why you were able to do that. We're not direct substituting in the whole thing. So if you separate it into two limits, we can do it here. If you say, I'm going to go ahead and substitute, you have to substitute it everywhere, and we can't just necessarily do that. Because we're going to have to change that guy around. Okay? All right. Now, okay, we're going to write cosecant in terms of sine. Okay? So let me get some more room here. All right. Could I write this as limit as x approaches 0 of x over sine 11x? Does that make sense? Because cosecant is 1 over sine, so we're good. Okay, what do I need? What do I need for this to look like to use our theorem? Because now I've at least got sine. Okay, now it's usually sine x over x, but since we're talking about 1, it's going to end up being the same. Even if I did the inverse, I'm still going to end up with 1 if I can make it. But what do I need this to be? 11x. So could I multiply both sides by 11? Okay, so do that. And what do we get? Whoops. I keep changing color. Okay, do we agree that's what we get if we multiply by 11 over 11? Is that good? Okay, so what can we pull out? I can't pull out this 11, right? Because I've got to have that 11x up there. So what am I actually pulling out? 1 over 11. So think of that as 1 right there times 11x, and I can pull out the 1/11th because it's kind of out in front. So I'm going to have 1/11th limit as x approaches 0 of 11x over sine 11x. And what's that going to be? Because even if I wrote this as an inverse thing, I'm still going to get 1. So I don't really have to do that. I mean, if I were proving, I probably would, but you just know that that's going to give you the same thing. So it's 1/11 times 1, which is 1 over 11. Okay? Okay. We good? Yes. Right here? Right here? Okay. What's going on before I wrote that, Dinah, is I had this, and I need it to just be 11x over sine 11x. So I'm going to pull something out, but I can't just pull out 11. There's something on top. So I'm actually pulling out 1/11, and then that gets rid of that part. Does that make sense? Okay, and did you have a question? Uh-huh. Well, cosecant's 1 over sine. Well, if you think about it, this is, it's x times cosecant 11x, thank you. And so if I now write it as x times 1 over sine 11x, so now the x is on top without anything else. And so that's how we got to there. Is that good? Okay. All right. Okay. All right, look at that one. Is there anything, I mean, do we have to do anything special to this guy? The limit as theta approaches negative pi of theta cosine theta. Is there any reason that we have to do anything? Can we just plug in? So, what do we get? Limit as theta approaches negative pi of, okay, so that equals negative pi, and then cosine of negative pi is what? Negative 1. So negative pi times negative 1 is pi. Do what? Oh, well, I didn't write, here, I didn't write the whole thing. I get real happy with my shortcuts. A minute, that's better. Formally, that's much better. Yeah. Okay? Good? Yeah. Cosine of pi was negative 1, and I just substituted negative pi in for that theta. Okay? Okay. I think we have one more. Okay. And got one on your homework. This one takes a little bit of manipulation, but I'm going to show you how we're going to do it, and then you'll have that down. The limit as x approaches 0 of tan 4x over sine 7x. Okay, what do you think we need to remember from our trig? Sine over cosine. So we're going to need to use that. Okay? All right. Let's see if we can follow this. Limit as x approaches 0 of, instead of tan 4x, I'm going to write sine over cosine. So I've got sine of 4x over cosine 4x times 1 over sine 7x. Is that fair? Is that equal? Can I do that? This is like tan times 1 over sine 7x. So that should work, right? Okay. It's not going to totally help me with anything. I need some other stuff. Let's see if you agree with this. Why would I want to do that? I need 7x over there, right? But I can't just arbitrarily multiply by 7x over 4x. I get to multiply by 1, so what do I have to multiply as well? Just 4 over 7? Do you agree that that's 1? Doesn't that all cancel out to be 1? Okay, so it's gonna help me. All right. All right, how we doing? How we doing? Okay, it's lost. Okay, so, sine 4x, could it pair with this guy? And the 7x can go there, right? Because I'm going to just kind of rewrite some stuff. And the 4, where can that go? It's going to go out. And the 7's going to go out. Okay, let's try to think about rewriting. If I move the sine x over the 4x, the sine 4x over that. Sine 4x over 4x. I'm just moving things around because this is all multiplying, right? and times 7x over sine 7x. 4/7 can just come out here. What do I have left? Okay. What does this become? Okay, so that's 1. What does this become? And what's the cosine of 0? 1. What's the answer? 4/7. Hold on, let me. Okay, so just to recap that problem, because you're going to have one on your homework, you know that you're going to make that substitution with tan, sine over cosine, and then you know that you've got to get some things changed around here, and that we had to do this just to stay legal in the math part. Dinah.
On that second step, what is cosine for x?
Here, right here.
I mean, like, we're going down to all the ones.
Oh, right here. As x approaches 0, cosine of 0 is 1. So it's 1 over 1. We just evaluated all 3 of these. Okay? Do not, okay, so that I think will get you on that one, but let me do this.